Okay, so I'll start with my presentation. I don't have too much of a flashy beginning slide, but it's titled The Wonders of Color Vision in Human Perception. My name is Alberto Ruiz. I am a third-year PhD student working out of the Thayer School of Engineering, and I work a lot with imaging medicine and optics in medicine. So sort of learning objectives that this talk has with regards to information that I want to share is asking that question of what are photons or light particles and how are they detected by the human eye, understanding colors and how they're really a human perception, and also appreciating the role of our brain in interpreting the visual world and how it can pull all kinds of tricks to make sense of the world around us. So what is light? So light is just electromagnetic radiation, and when we look at it in the full amount of spectrum, it includes gamma rays, X-rays, which are used in CTs and X-rays if you go to your dentist, ultraviolet. Then we have that little sliver of visible light, which we can detect with our eyes, and we'll talk about that a little bit more. We have the infrared, which we can associate with the heat coming off of incandescent light bulbs, and we also have microwaves and radio waves. And 5G, wireless, all of it is just light particles that go from one place to the next. And we're going to focus on this little sliver of visible light that we can detect with our little eye detectors. So again, here it's another way of visualizing it. Really, the difference here between one light particle and the next is how small of the wavelength it is. That also gets correlated with the amount of power that is associated with it. And we can see here some of the different applications for the different wavelengths of light. And you also associated with increased energy, including gamma rays. So you don't really want to be around those because those can break apart the DNA. But for the visible light, we're safe and we like looking at it with our eyes. And that's what we're going to concentrate on. So how does light travel and what are photons? So light is self-propagating. So it doesn't need no medium, which is really nice. That means in space, it can still travel. If you think about waves in an ocean, they need the water in order to travel. If you think about sound waves, they need air in order for those pressure waves to travel. But light doesn't need any medium. It's just self-propagating. And that's a whole other fascinating talk in itself. And light can behave both as a wave and as a particle. So here's a little visualization. If we talk about light behaving, so we're all familiar with the prism, right? Splitting colors into different lights. But two ways to visualize this is visualizing light as a wave, and we can also visualize light as these little particles. And there's interesting physics that works out if you include them into both. And there's things like everything is sort of a wave, but we're going to focus on this photonless light particles because it facilitates that discussion about how we detect these light particles with our eyes. So how do we really see things? We have the human eye, which is a photon detector. And what happens is our cornea, pupil, and iris serve as our little camera lens. And then we can project that image onto the retina and these different sensors that we'll talk about a little bit further. But then a huge other role is we have our brain as this imaging software that interprets off these signals. So all these signals are very complicated and our brain tries to make sense of them. And that's how we're able to detect different colors of light. It's really through this interaction of the eye as a detector of light particles and our brain as an interpreter of the signal that we're getting from the eye. And we'll go into some demos about how your brain can also play tricks in trying to get to make sense of what the eye is trying to detect. So, you get a photon, it bounces off a bird that goes into your eye, and really it's in the brain is where all this processing takes place to create this image of the bird. And how we detect this is through having pixels in our eye. So there's two categories, there's cones and there's rods. The cones, there's three different types, and that's what enables the color vision. And the rods, they're sort of grayscale and they allow low light vision. So that's also why when we take a look at things at night, we can't really see color because the ones that are low light detecting don't have that ability to variate the color perception portion of it. So if we take a look at our eye, we have the fovea, which is where the center of the image is. And if we zoom into that fovea, we see these little pixels in the eye. These are the cones. And there's three different types of cones. There's the short, medium, and the long cones. But in the end, you can think about it as our own little personal blue, green, and red pixels. And by the different signals, the eye can detect the different colors. If we go in and zoom in, but also get away from the fovea towards the sides of the eye, we start seeing some of those rods embedded within the different cones. So in the center of your eye, it's really good for high definition color vision. And as we go away from the center of the eye, that's where more of the rods start popping in and less of that color vision. And our brain brings that all together. And here's also the spectral response of what colors the rods like to detect. So generally our eyes are best at detecting green light because of this aided help that the rods also bring into its image processing. So, okay, we have these cones and these rods and we can generate colors, but how does that really work? So the easiest way to visualize this is what's called a chromaticity diagram. And what they allows us to do is visualize these color spaces, and they let us see all the hues or colors that the human eye can see. So if we think about the normal rainbow spectrum, those colors lie on the edge of this chromaticity diagram. So these are saturated colors. So if I see a little red laser, for example, which is normally about 650, 670, it'll look about this hue of color right here. What we also have here is what's called the black body curve. And this is what we associate with daylight colors. So if we take a look here, this 3000 K, so 3000 Kelvin, this is what we associate with more incandescent bulbs, and 6000 K is what we associate more with fluorescent light bulbs, like hospital, clean bathroom sort of look. Modern technology now has light emitting diodes or LED lights, which can mimic all of these colors. So this is also a slight pitch to not buy incandescent light bulbs because they're not energy efficient, and LEDs can also do the same job, and you can buy them at the different shades of colors. I'm a fan of the 4000. A lot of people like the 3000. I'm not here to judge anybody. But one of the really cool things also, if you have a hue changing light bulb, what you can do is if you have a light source that has a blue emission, also a green emission and a red emission over here, you can mix those at different ratios and achieve any of the colors that are within this triangle. So if anybody has ever bought or seen one of those like Philips Hue light bulbs and they're able to switch between different colors, you're just changing the ratios of these blue, green, and red light sources within the light bulb itself. So another cool thing about this, though, is that your eye is really good at interpreting things, but a lot of times it tries to make things up, which means that for two different light sources or combinations thereof can make the same color. So in this little demo, we have this color A and B, and if we add them up at different ratios, we can achieve any colors along this line, right? If we add a third color, maybe over here, you can achieve any color within the triangle. But now let's pretend we also have these light sources that have these particular wavelengths, so D and C, right? You can see that in that interception right here, if I make it so that D and C have a ratio that lands right here and A and B lands that ratio right there, your eye can't tell the difference between those. So even though you have two different light sources that might be made up of completely different wavelengths of colors, fundamentally, if you mix them together, your eye doesn't know and it doesn't care. Right? It just says, hey, it's about around this color and you're getting this amount of ratio. So we're not really a scientific equipment with regards to our eyes and our brain. We're just really good about living around our world and saying, well, these hues and these colors interpret in different ways to make sense of the world. So when we think about color in computers, we normally talk about RGB values. And if we go back to this diagram, what happens is the display that you're looking at right now is composed of little small pixels of red, green, and red in little units. And you can change the relative ratio of those units to recreate all these colors. But fundamentally, what's happening is you have a blue, a green, and a red, and you can have different color spaces, depending how much money really in the end you invest in your monitor. And you can mix those colors to make colors within the triangle. So if we take a look at your PowerPoint presentation and you look at a color, we see that our RGB values are right here. And then we also have a concept of brightness. Now, what this means is that you can have pretty interesting things that mean, even though you have the same hue or in reality the same color, these have the same color, but the lightness or how bright it is changes our perception of it. And so what happens here is, if you can think about it in a room or in your living room, if you see a couch and it's sort of blue and it's a light blue, if you dim your lights out, that blue is going to get a lot darker. But in reality, you're seeing the same color. It's just our perception changes based on that brightness of the source and what we're looking at. So I want to transition to do some visual adaptation demos, and this is to emphasize two things really: the beauty of our brain and how it can interpret all these things and make sense of the world. And then the other thing, in some ways, being skeptical about always trusting what you see, because your brain does all types of magical processing to try to bring about the images that we see. So for this first image, I want you to look in the middle of these colors, and I'll switch it in about 10 seconds. So just concentrate right in the middle intersection between them. Right, and then I just switched, and you can see this floating colors, but in reality, I haven't switched anymore. Right, if you look, when you look back, it's actually all white, and you can still see it there, remainders of that color. Right, and that's crazy. And I'll switch between the two kind of fast, and you can see that there's no colors in this one, yet my brain now still has some sort of memory that I'm supposed to be looking at these hues, and it blends it in with that white in the background. So that's a beautiful way of your brain. You've been looking at something for so long that it doesn't expect movement. And as I switch from one slide to the next, it expects to see sort of the same hue because your eyes haven't really moved and nothing on the borders have moved completely. So it tries to reinterpret the colors that it's seeing, even though they're actually not really there. This next demo I love. This one's a little bit harder to achieve, but what I want you to do is center your head on the screen, or if there's more than one person, take turns. And you want to close your right eye, but focus your eye on the plus sign. And what's going to happen is you're no longer going to see the circle. And if you can still see it, either go in closer or go in farther. And if you also do that, you'll start seeing the circle again. Again, focus. You want to close your right eye, center your head on the computer, look at the plus sign, in this case with your left eye, because that's the one that's open. And if you go in and out, you're going to start seeing the circle there, but it also disappears in some section of it, right? I don't know if people are able to do it, but the idea here is when it disappears, our eyes have a blind spot that's associated with the optic nerve is. And so we don't have any of our eye pixels. And so what our brain is doing all the time, when you have one eye or both eyes, it's composing an image of what it thinks that it's going to look like there. But in reality, there is no information to be had there at all. It's just there's no sensors at that point in the eye. And so our brain is doing this magical scenario of doing it. And I guess by anybody who's not able to do it, we can try to walk it through. There's not a bunch of people in the meeting, so we can try to do it. But again, if you weren't able to do it, you want to hold it, maybe a foot or 2 feet away from you. You center your head on the screen. You close your right eye. You focus your sight on the plus sign, and you keep it there focused. And if you move in and out closer, and you can look at me while I do it, eventually, if you do it slow, there's going to be a point where that circle just disappears. And it's fascinating every time. It still gets me. I do it all the time. I probably do it more than I should. But it's that fascinating of how your brain can just compose these images even when it doesn't have any information. So it's fascinating. And you can email me if you want to walk through it individually if it didn't happen, because it's one of my favorite things ever. This other one, it's a little bit nauseating for some people, but we'll do it anyways. So what's going to happen here, there's going to be a motion. The circles are actually going to remain not moving in any X, Y, or lateral position. They're just going to rotate, and then we'll play it and we can talk about it. So here it appears that they're moving in together. Here it appears that they're moving apart, but obviously they're not really going out of the screen. So, what's going on now, it's just like one's increasing, the other one, that's crazy. So we'll go back and let's try to play that again, and I'll add in some lines. So what it turns out is that the circles are never moving in that lateral motion, but our brain is trying to interpret that rotation and the direction of the arrows as motion of some kind that we associate abstractly. This is not even something that happens in nature. At this point, this is a human-made, what we have all agreed to as what an arrow looks like and what it means in terms of direction of movement. And so we'll play that again, and I'll play that again even with the lines there, on how our brain can do this magical scenario of saying, I expect it to go that way. And these optical effects are often associated with our brain trying to make sense of the world, but sometimes being tricked into seeing things that are not really there. So to wrap it up, human vision is absolutely awesome. Light is part of the electromagnetic spectrum, and we detect them as these little particles of light using different detectors that we have in our eyes. But it's really this coordination of the eyes and the brain that work together to generate color by detecting these light particles. And the brain performs all kinds of tricks to adapt vision and make sense of the world. So that is the end of this talk, and I'll be happy to take any questions that might be had in the meantime. Yeah, human vision is dope. It's cool.
That was so cool. That was
yes, Sarah.
So you showed that crazy picture of the 4 different colored squares and how it kind of keeps your kind of sensory processing even when it's adapted to these blank squares. Do you think that there's like an evolutionary benefit or an evolutionary disadvantage to this kind of delay in processing? Like, does it increase stability, or is there something lost that we take so long to kind of shift?
So this is completely speculation, but I think a lot of what the human vision has evolved is to be able to detect motion. And so we're often like, our brain is always trying to be like, is something moving, right? And so in that case, it's sort of what happens when it's trying to dedicate itself to detect movement, and how it's tricked to try to look at things it's like, I don't see any movement, and others is the thing that it's not matching. So from an evolutionary perspective, I think it is remnants of optimizing for detecting movement, and it's just some of the side effects that end up happening because of that.
Awesome, thanks.
Cool. Okay, so if we don't have any questions, we can transfer to our second talk by Georgia. And I love this talk too. So
Alberto, those are so cool. I remember the first time you showed those to me, I literally screamed. Like, I was so glad my mute was on because it was so shocking. Oh, they're so cool. Okay. I'm sharing my screen here. But hello, everybody. My name is Georgia, and I'm a grad student here at Dartmouth. And wow, we just saw those crazy things that made us question whether we should always believe what we see and take it so literally. I want to pivot and show you a little science that might make you ask whether you should believe what you hear. And this isn't what I'm studying or the research I'm doing for my degree, but it is one of my favorite papers that I've seen in the past couple of years. So I'm really excited to be able to use this piece of primary literature as an example of how we can engage with scientific literature and also assess it and begin to understand things using data of different types and make decisions for ourselves as to what we're going to believe and what we're not going to believe. Okay, awesome. So the title of this piece of peer-reviewed scientific literature is Imitation of Novel Conspecific and Human Speech Sounds in the Killer Whale Orcinus orca. And it was published in Proceedings B of the Royal Society Publishing Group in 2018, so almost 3 years ago now, by Abrams et al. And while we're not going to all sit here and silently read this primary literature together, I want to introduce you to the paper a little bit. So I copied out the title and I subbed in the definition of conspecific, which just means same species. And that was a piece of jargon that I actually hadn't heard before I read this title and had to look it up. And so you can also read it as imitation of novel orca and human speech sounds in the killer whale orca. And what I've cropped out here is the first sentence of their abstract, which is often the very first thing one would encounter when reading a scientific article. So I'll read that as well. That reads, vocal imitation is a hallmark of human spoken language, which, along with other advanced cognitive skills, has fueled the evolution of human culture. And to me, that sentence really evokes the power of spoken language and what it means to be human. But I also looked a little more closely and I distilled for you the major claims they make in their abstract. And those major claims are that the killer whale makes recognizable copies of novel sounds from both humans and whales. So a little less ambitious than identifying a language of communication and culture in an orca, but yet still some pretty tall claims. And now that I have kind of clarified those, before we go any further, I wanted to take everybody's temperature as to their initial reactions to that title and those claims. So I put this bar on the bottom as a little barometer that ranges from optimistic to skeptical. And if everybody goes up into the, goes up into the Zoom bar, down, goes up into the Zoom bar and presses the view options, there should be a drop down that then says annotate. And if you open up that annotate toolbar, there's a tool called stamps and it looks like a little check mark. And if you click on it, there's, yes, good job, Alberto. There are 6 different little shapes you can, and you can choose any of those. But using those, would you please mark on this bar where you fall with respect to your initial reaction to this paper title? And, while people are figuring this out and maybe putting up some reactions there, I will say that I think anywhere along the spectrum is a completely valid opinion. And I kind of put the kind of spoiler alert here. But so perhaps you've heard of Coco, the gorilla who's proficient in sign language and makes friends with kittens and likes to read her own little biography there. So to you, the idea of an animal adapting human language is no big deal. Or perhaps you're a fan of the Dr. Dolittle franchise. And to you, the sheer absurdity of animals speaking human language lends enough comedic power to fuel a successful movie franchise. And so all of our different experiences and background knowledge can contextualize us. And that's why we all have different initial reactions to a statement or a scientific claim. But I don't want to kind of make fun of this claim. And I do want to acknowledge that it falls within the context of a rich scientific history, and that studies of animals using human language date back decades. In the 60s, there were some real breakthrough studies teaching apes and dolphins how to speak human language. And there were some successes as well as some kind of spectacular failures. And then there was kind of an acknowledgement of the difficulty of what we're asking animals to do. With respect to the physiological differences, right? So we have our vocal cords, we have our mouths and our tongues, and we have lots of machinery that we can use to make different tones and sounds. And orca, like dolphin, they have an organ up in their nasal passage called phonic lips that they can use where the muscles can contract to create different tones. But these are very different organs adapted to very different environments. One thing that's really cool about the phonic lips is as an orca swimming through the ocean and encountering different depths and different water pressures, they can still very intentionally create a very specific tone. So they have to be able to adapt to that. And that's not really something we encounter, right? And so language studies took a bit of a turn, and they began to adapt things like symbolic language and sign language. And here there was a lot of work that began to associate language and intelligence, right? And I think that this body of work certainly influenced my initial reaction to this Title. However, when we looked closely at the claims, we found that this paper is really an acoustic analysis that harks back to earlier papers, where they're not assessing the orca's intelligence or ability to communicate. They're assessing its ability to create human sounds. And in this way, they can kind of assess its ability to mimic really intricate and new and complex activities. And so I think that that's kind of the heart of this paper. And it's only possible because, for years, orcas have learned to mimic actions like flipper up or, splash in the pool and things like that. So they can already mimic actions, but can they mimic intricate noises and intricate sounds that are meaningful to us and not them? So what's their experimental setup? They have a do as I do paradigm here, and they test their subject orca, who is named Wiki, in 3 different ways. The first test has Wiki in the pool as the subject, and behind a physical barrier so they can't see each other has Wiki's daughter, Moana. And they signal to Moana to make a noise, like a raspberry or a whistle. And then they signal to Wiki a very specific gesture that they've trained Wiki on, which just means mimic or repeat or imitate. So after they do that gesture, they can record the noise Wiki made as her imitation. So, and they can also do that with like a speaker. So Wiki can be in the pool alone and they can play a sound. And this way they can introduce novel sounds from orcas Wiki's never met and never heard before. And then again, motion for Wiki to mimic and record the response. And the third, kind of most ambitious experiment they do is they pair Wiki with a trainer who simply vocalizes a human word and then symbols for Wiki to mimic again, and they can record the response. Here's Wiki and Moana in their pools. You can see that the whole time they kind of have their heads up out of the water. And I think that that's kind of important to acknowledge, that these whales are kind of doing these performances in not necessarily their native environment, but anyways. So here they are, and we're about to go into the results. So I just want to add that if anyone feels the desire to kind of re-annotate their optimism or skepticism based on either the background knowledge or understanding the experimental setup, feel free at any time to kind of edit how you feel. And I think it's interesting to kind of keep track of how our opinions can change and how that's completely important for science. Okay, so I'll show you a result. This will be fun. I'm gonna play a clip, and this clip has 4 vocalizations from Wiki, and I spliced them together, but they are 4 vocalizations that were collected independently in response to the same model or the same prompt. So I'm gonna play them, and then we'll see if you guys can guess which of human words were the prompt. Does anyone, if you still have your annotation tool up, want to kind of take a guess as to what they think those were? I'll play them again. Aha, nice. Hello. Amy. Yeah, it's really fun. I guess I'll give away the answer so we can see. This was in fact Amy. And now I will play a recording that has the human word prompt and the response right next to each other, so you can do a kind of direct comparison of those sounds.
Amy. 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 Amy.
And well, I could spend probably all day listening to these recordings. I don't know if I could make a rigorous scientific claim about their similarity or difference to the human word. And perhaps feeling similarly, the authors chose to present as their primary evidence, not necessarily these recordings themselves, but a quantitative analysis that was based on these recordings. So, taking these recordings, they extracted features that they could record quantitatively as numbers in order to be able to compare two recordings. So here I'm showing graphs of a clip. This clip is of the model human saying Amy, and then Wiki's response labeled as the copy. And the top and bottom graphs are of the same clip, just to show how they can extract different audio features from these clips. The top one you might recognize from like SoundCloud or iTunes, and it kind of represents different bursts or tonal change in and dynamics, right? So that's one type of feature. The colorful plot on the bottom actually represents different tonal features. So the hertz on the side that range from 0 to 8,000 are different tones, right? Like do, re, mi, fa, sol, la, ti. Like I don't need to sing for everybody, but those different tones. And then the color is an intensity. So across those 0.8 seconds, there could be more low notes or more high notes. And they record all of this, and they take all of this. They take up, I think, 12 features, calculate them all together using some pretty advanced like mathematical transformations and techniques. And they come up with a single number that they call a dissimilarity index. And this is what they use to really prove their point. So in this result, which is really the major result of their paper, they're showing the dissimilarity indices calculated for different pairs of recordings. And in red, the first thing I'm showing is the controls, which is a very common scientific tool to use in order to orient our results. So to whether to say a result is good or bad can be a subjective relative thing. So instead what we do is we take things that we know should be good, like matching a human saying hello to a human saying oh, hello, and we make that our gold standard. So we give it a dissimilarity index of 0. And then we take things that we know are bad, like mismatch words, a recording of Amy and a recording of 1, 2, 3. And we call those our negative controls. And as you can see, they have much higher dissimilarity indices. And so the authors then came up with this threshold that falls below all of the negative controls that they decide is their threshold for a recognizable copy. And then any dissimilarity score that falls below this threshold can then be considered a reasonable recognizable copy. So now let's get to the data. And the first data I'll show you is Wiki's imitation of other orca noises. And here they are. And you see that they all fall below the threshold of recognizability. In blue are sounds that they were sure Wiki was familiar with and had heard before. And in green are sounds generated by other orca Wiki had never met or encountered. So it's interesting to see that the familiarity of a sound doesn't necessarily mean that Wiki's going to be better at copying it. Yet, all of these, as a group, all of these imitations fall up within the recognizable range. And then, of course, there are the human mimics, which are a bit more of an exciting result. And again, all of the human sounds fall within this recognizable range. However, there is a big spread, right? So some mimics of human words are even better than mimics of orca sounds, right? And then some of them are kind of approaching our negative controls. But this type of complex and variable data is to be expected in these real-time experiments using this orca subject. And overall, they found a way to frame their comparisons in an objective or at least quantitative way with which they could argue that Wiki had made recognizable copies of novel sounds generated from both orca and humans to support their title. Now, if you really like plots, you may be super convinced by this graph. However, if you're like me and you prefer to listen to orca recordings, you may be curious, like, just how good is a recognizable copy? And so far, we've only listened to one example. So now I'm going to play a longer clip, and this has all the different examples, so we can see the range of how well Wiki was able to mimic these sounds. In this clip, you'll hear a prompt that was either an orca sound or a human word, and then you'll hear a beep, and then Wiki's response. So that beep separates the model from the copy. And then it will show the series of those different prompts going down, first the orca sounds, then the human words.
Hello? Amy. One, two. 1, 2, 3. Bye bye.
I don't know about you, but I just find those recordings incredible and amazing. So now we're presented with the question, given that data, both the quantitative and the qualitative recordings themselves, are we convinced? Has Wiki imitated orca and human noises to a sufficient degree? And again, I kind of left this annotation box up. It looks like a lot of the kind of views of the paper were fairly optimistic to begin with, which I have to confess, when I read that title, I said, no way, right? I was very skeptical coming in. But yeah, so it's possible that maybe you all are a little more convinced, or maybe you were optimistic, but that data was just not very compelling and you changed your mind and you think that those recordings were not reasonable mimics of human words. But either way, when we ask ourselves whether a paper has supported its initial claims, it's also important to ask ourselves which type of data was most compelling and what caused us to change our opinion. So was it the quantitative analyses, or was it actually listening to the primary data along there? And this is kind of my final slide. So if anyone wants to annotate or make a comment or an opinion, feel free. I would love to hear everybody's thoughts on the matter. Yeah, I know. I have to confess, Wiki did pretty well. There are a couple things, like if you look closely into it, she's a pretty high performing orca who's been used in multiple studies before. And so she is, while this study may have very successfully shown her ability, she also might be a pretty special snail. And so that is what brings me to my final slide, which is really attributing credit to our subject here. And so Wiki is adult female orca, born in captivity, raised in captivity in the Marineland Aquarium in France. She has born multiple children, 2 or 3 in captivity successfully. She has been separated from some of her children as well. And while this paper has provided me with a lot of information and thoughts and entertainment and engagement, it has also come at a pretty big cost. And that cost is summed up in orca captivity overall. So I do want to end with kind of putting some links in the chat to more photos of Wiki, if you would like, but also to an activist agency dedicated to helping end the impending extinction of the southern resident orcas out on the West Coast, which is a serious problem. I will say that the shirt I'm wearing, these are Southern residents right here. So these are kind of the real deal, wild Southern resident pod right there. And they do hold a kind of a special place in my heart. So thanks to Wiki, thanks to Alberto, thanks to all of you guys. Here's the paper again, and I will stop sharing so I can put some things in the chat.
Any questions associated with the last talk or the Science on Top series overall? We're hoping to do one every other month. That's what we're trying to aim to do. So the next one might be in January or February, but we'll keep everybody posted.
Oh, okay. I guess Dallas posted the links. And I will say one of those links has a video of these tests going on. So that CBC link is very fun to watch. But yeah, okay. Thanks, Alberto. Thanks so much. Thanks for all of you guys coming.
Thanks, everyone.